A meme of introductory physics teachers that's been around since before memes were called memes is that of a teacher rebuking a student for using the phrase centrifugal force. When the class gets to circular motion, the student learns about another force, sounding very similar and having the same number of syllables, and generally walks away with the notion that the teacher just wants them to use the phrase centripetal force instead, and that the whole distinction is a matter of semantics. That we settle for this is a huge disservice to the student and a missed opportunity for the laws of the universe to be seen. In this video, I'll explain what a centrifugal force is, why it doesn't exist, and why your experience of it is real anyway.
There's an old joke about a retired couple. A concerned wife is watching the news and calls her husband saying, "Honey, are you on the highway? Be careful, the news says there's some maniac over there driving on the wrong side of the road." To which the husband replies, "One maniac on the wrong side, there's hundreds of them." The basis of the joke is how the husband manages to maintain an explanation for his obviously wrong viewpoint instead of going with the far simpler narrative that he's the one disobeying traffic laws. Centrifugal force is essentially this, a more complicated explanation that allows us to maintain a certain non-standard viewpoint. Why do we have the urge to entertain that viewpoint? Well, it goes back to the way our brains have learned to do the physics of everyday survival. Caveman brain is actually quite good at intuitive physics, and so we, understandably, have a lot of confidence in what it predicts to the point where certain misconceptions linger for the majority of people, even after they've taken a well-taught physics class. One thing we intuitively believe is the law of inertia, which means that objects don't start moving without a force acting on them. Which would be fine, but another thing we believe in is the validity of the reference frame we're inside of. Your own frame of reference being valid is mostly true, by the way. Sitting on an airplane going 700 miles an hour, you don't really have to stop and think about that motion to toss a ball to someone. You just pretend as if you're not moving and everything works out fine. In fact, Einstein's special relativity says the laws of physics will be completely identical as long as your reference frame is moving at a constant velocity, meaning constant speed with constant direction. But this breaks down when you're not. An example. If you're standing around and your friend pushes you from in front, there's no dispute. You've just been pushed backwards. Yet put yourself in a fast-moving car with no seatbelt on while someone slams on the brakes, and you get the sensation that you've just been pushed forward out of your seat, even though anyone outside the car could clearly tell you that the car's tires have just applied a large backwards force to make the car stop. What's happening here is that because you're surrounded by 2 tons of steel and glass and an entire car interior that's moving with you, you get the sense that your viewpoint, or frame of reference, is just as valid as someone standing on the sidewalk outside. Throw the law of inertia in there, that things don't accelerate without feeling a force, and you'll conclude that some magical invisible force was pushing you forward out of your seat. But what's really happening is caveman brain is trying to make his frame of reference legitimate, just as the husband's explanation of wrong-way drivers is trying to make his frame of reference legitimate. The same thing happens in a rotating reference frame, such as a car making a sharp turn. We again try to make the car's interior a standard reference frame and figure the law of inertia works there, i.e., things only accelerate when they feel forces. And then strange things start to happen. We make a right turn and that coffee mug sitting on the dashboard gets pulled to the left. There must be a force doing this, we think, and we call that the centrifugal force. There should be things that tip us off that this force isn't real. All forces experienced by an object are caused by another object. What object causes this centrifugal force? What object is even touching the mug that slides across the dashboard? And isn't it strange that this force seems to act at the center of mass of the mug rather than at its surface? So what's really happening here if there is no force? The car is rounding a turn while the mug continues to drift in a straight line. The car is just moving out from under the mug while the mug follows its straight line path. Another example. A roller coaster does a vertical loop. What keeps the passengers from falling out of their seats? From the reference frame of the passengers, there's a magical force keeping them up. But seen from outside the roller coaster, the passengers are falling. In fact, they're being pushed down by their seats. And yet, if you're willing to do a bit of linear algebra calculus and vector identities, you can represent this imaginary force with math. Linear algebra gives us simple rules for simple coordinate substitutions like rotations. Whenever your yoga teacher tells you to raise your left foot while raising her right foot, She is doing the coordinate substitution of rotating herself 180 degrees to your viewpoint. We have the math for this kind of viewpoint change because the laws of physics are perfectly valid for any reference frame that's rotated from another one. But going around in a circle is nothing more than a continuous rotation of your viewpoint. Even if the apparent laws of physics will be affected by continuous rotation, there's nothing innate to the math that means you can't look at the same spatial information from a rotating viewpoint. So we can separate out the motion in the rotating reference frame into an object's position relative to a fixed axis and the object's position relative to the rotating coordinate axis. Since this gives us an expression for position, finding the acceleration is just a matter of taking a couple time derivatives and applying the rules for time derivatives in a rotating coordinate system. The result is one term that looks like the second derivative of position in the new coordinate system, and then three other terms that are all related to the speed and direction of the rotation and its change. Now that we have an acceleration, we can write Newton's second law, F equals ma, using this A. Here's the jump. We pretend that we are unable to see any rotation in our reference frame. We are in the interior of the car and only interested in acceleration relative to that frame. In practice, what this means is we take those three extra terms we picked up that involved rotation, multiply them by mass, and then subtract them so that they appear on the other side of the equation. It's a very simple algebraic operation to subtract the same thing from both sides, but from a physics standpoint, this is a revolutionary act. We've done nothing less than declare those terms to be forces that cause motion, rather than a description of the motion itself. You get F plus some magical new forces equals ma. Each of these three terms we recognize as a force. The first is just a reaction to your rotating reference frame speeding up, called the Euler force. The next has been coined the Coriolis force, which is the reason storms rotate the way they do, and many erroneously believe is responsible for the direction of toilet swirl. And the last is the centrifugal force, an outwards force that seems to be pushing on all objects in the rotating reference frame with a magnitude of m times omega squared r, where omega is the rotation speed. So if you do all this math, you are actually free to treat the centrifugal force as a real force, and you will get the exact same results. You will get the physics right. This imaginary force causes motion that you can predict mathematically, and your predictions will be correct. There are tons of examples in advanced physics when treating the centrifugal force as a real thing brings clarity to problems that would otherwise be hard to model. But given the amount of work it took to get there, can you really blame your high school physics teacher for not wanting to teach you coordinate substitutions in calculus when they're likely struggling to get you just to write units on your answer and stop believing that constant force causes constant velocity? So in the meantime, they settle for a much simpler answer of don't do physics from a rotating reference frame, and all these magical forces you've dreamed up will evaporate like fog in the morning sun. Once you can do the basics, maybe we'll get you there your sophomore or junior year of your college physics major. Driver's education doesn't start with learning how to drive down the wrong side of the highway. So thanks for watching. Remember to stay coffee snobby.